Okay, this is linear algebra part 1 lecture. Okay. So before I start, just so you know, like if I go through things like in kind of a weird way or don't explain it very well, just let me know. Because I often have that issue. Okay. So the whole concept of linear algebra is focused around vectors. So if you've taken like a physics or calculus class, you've probably been introduced to the idea of vectors, whereas like if it's through like vector equations or free body diagrams or whatever. And particularly in physics, if you do like free body diagrams.
We'll cut this.
Yeah. So like particularly in physics, when you're dealing with free body diagrams, you're just simply adding vectors and seeing like the magnitude of the vectors, but you can do a lot more with vectors than just adding them and like looking at their magnitude. You can actually like transform them and scale them and do whatever you want with them, basically. And so, like since the entire idea of linear algebra is basically centered around vectors, too, I'll try this. And vectors basically have two properties. They have a direction, and they have a magnitude. So if the way we normally write vectors is we usually have any letter, whether it's like an A or B or C or usually it's a V just because that's what vectors are. And they have a little arrow on top. And this right here is used to denote some vector, and we don't know what this vector looks like. We just know it's a vector. Okay, so the way we write vectors, it actually varies between class to class and how you want to write it. But vectors essentially have coordinates. So the way the vector works is, so a vector has two coordinates. It has an x component or x coordinate and a y coordinate, just like a point does. And so literally all you do is you just go to your xy plane, and the way it works is your tail of the vector is fixed to the origin, and the tip is wherever your coordinate is. So in this case, this is A and this is B. So this is what your vector looks like. And that's essentially what it is. It's just, you just keep your tail at the origin, and your tip is just fixed, it's just put to wherever A and B are. So that's kind of the general idea of what the vector looks like. But there's actually multiple ways of writing this specific vector here. You could write it as, like I just mentioned here, you could write it as A, B in this little box, which is actually called matrix notation. You could also write it as A and B with these kind of greater than, less than brackets. And there's one more, you can actually write it as A I hat plus B J hat. And this one especially is what I'm gonna get into, because that's extremely important to understanding like the matrices and so on. So, all right. So there's a lot of things that we can actually do with vectors. We can add them, we can multiply them, we can scale them, we can transform them. We can do a whole bunch of stuff with vectors. So I'll start with some simple vector properties, like with scaling, for example. So here's a scalar. A scalar simply is just a number that you put in front of a vector. A scalar is just a number you put in front of a vector to basically make it larger. So it doesn't change the direction at all. All it changes is the magnitude. So a scalar C, I'll just call it C for now. Simply what you do is you just, the C multiplied by, or the vector multiplied by the scalar simply just increases or decreases the length of the vector depending on what C is. So if C is 2, it just doubles the length of the vector. If C is 1/2, it just halves the length of the vector. Yeah.
Was it like the vector by itself doesn't have an inherent length then, it's just talking about the direction, and then the scalar just determines like the magnitude in that direction? Or
no, the vector also does have a magnitude, but the scalar just changes the magnitude of the vector. And
so this is not like it's not saying that it's like that direction with that magnitude. It's just saying that it's like that's the normal direction and magnitude, and then you're increasing just the magnitude.
Yeah, the only thing you're increasing with the scalar here is the magnitude. So
Is the inherent magnitude of the vector always the same as 1, or is it different?
So no, the vectors can have any magnitude whatsoever. The vector magnitude is just the square root of a squared plus b squared.
Okay.
It's just your like Pythagorean theorem. And so it could be 1, it could be 1,000, it could be whatever. Yeah. And so essentially that's what a scalar is you're just scaling the actual magnitude of the vector.
The vector always starts from the point of 0, 0?
Yeah, so the tail of the vector is always fixed at the origin.
That makes sense.
Wait, what?
That makes sense.
Yeah, and then the tip is wherever your coordinates are. Okay, so scaling vectors is one thing that you could do. So if you actually wrote this out, it would look like C times AB, which ends up just being C times A and C times B. And that's just what you're doing is you're just scaling each of the coordinates. Okay, there's also a couple more that we can go over. Adding vectors is a big one. And this is what this is going to do in just a little bit. So if we were to add vectors, what we can do actually is simply all we do, and let's say I add vector v and I add vector w. I add these two vectors, and let's say that vector v has coordinates a and b, so that this guy has coordinates c and d. Literally all you do is just vector v plus vector w is just, and you add these two coordinates together, so it's a plus c and b plus d. So if we look at an example of what this looks like, if we were to draw this out in a graph, and I'll give an example. I'll actually say that, let's see, vector v is 0, 1, and vector w is 2, 2. So, and I'm going to add both vector v and vector w. So this is vector v right here, and vector w is this. And essentially what this looks like, this is what it looks like algebraically. And so algebraically our final vector v plus w would just be whatever this is. So it's just 0, 3. But what this looks like graphically is you're taking the
0, 3 or 2, 3?
Oh, 2. Okay. Yeah, 2, 3. So what you're essentially what you're doing is you're taking the tip of this vector and you're bringing it over here, and so now this is also a vector v. And so you're just adding it on here, and you can do so. You're basically taking this entire vector and just bringing it to the end of this vector. Yeah.
Can you just draw a simplified vector like from the origin to the tip of v to just show
like this up here? You mean?
Yeah.
Yeah, exactly. That's the end. That's the ending vector is v plus w, and so this is kind of a so it's just a triangle here, and you're just adding, and you can do the same thing. You don't have to translate v and bring it up here. You can bring w and bring it over here, and it does the exact same thing. And so if we did w, it would. I'm actually going to draw this out again. So here's 1, and here's w, here's v. We can either do this, and we get this, or we can do this, and just get the exact same answer. And so here's our final vector. Just creates a parallelogram. So that's the general idea of adding vectors. And what we can actually do with this is we can represent vectors using we can just represent them as a sum of other vectors. So vector 1, 2 could be equal to vector 0, 1 and 1, 1 basically. And so that's essentially the idea of what I'm going to introduce here. The unit vectors. The unit vectors are literally just, there's 2 of them in 2 dimensions. There's 2. There's I hat and there's j hat. And I hat is the x unit vector, which is 0, 1, and 1, 0, and j hat is 0, 1. And so what these 2 vectors look like these two basis vectors. Here's j and here's I. And that's all it is. And the whole point of these two unit vectors is that we're able to represent essentially any vector we want by saying we can scale each of these vectors in some way, and we can add each of these scaled vectors in some way to create some final vector. So for example, if I wanted to create like some vector v, which was, I don't know what this is, 3, 3. That would be the equivalent of me saying I want to take vector I and scale it 3 times in this way, and then add vector v, or vector j, which is scaled 3 times in this way, which should, yeah, whatever. It should end up there. And so what we're doing here is we're just saying, okay, vector v, which is 3, 3, is the same thing as saying, okay, I'm going to take 3 of the I vectors, and I'm adding that to 3 of the j vectors. Yeah. And this is actually really, really important when it comes to the concept of matrices, is seeing how you can basically take any vector and break it down into components of just I and j, depending on the scalars. All right, does anyone have any questions?
That makes sense.
Okay. I'm gonna have to erase this because this next topic is gonna be a little bit bigger. All right. Okay, I didn't think we would get this far, but I'm actually going to introduce something completely different that you can do with vectors. I told you that you can add them, scale them, multiply them. We didn't go over that, but you can also do something really interesting, which is just like transform them. You can just literally take a vector and just move it around some random place, and you can do that in 2 ways, right? You can, and any combination of the two. You can either rotate it some angle, or you can scale it some way, and you can do any combination of the two. And so let's say I was, and so what we can do with this actually is we can, here, I'll just go. Okay, so let's just imagine that we originally had our I vector and our j vector here, like just our normal plane. Here are my axes, here are my grid lines, right? And these are my square grid lines that you have in the regular Cartesian coordinates. And I'm going to draw a little arrow over here. Okay, and let's say that I wanted not to have my plane look like this, but my plane have grid lines that looked like, let's say that like the y-axis was fixed in place, but now our x-axis is rotated 45 degrees. So now we have these weird grid lines that are kind of, parallelograms that look like this. These are my grid lines instead of the initial grid lines that are just squares in our regular coordinates. And how we can actually represent this is we can say, okay, what if we just took a look at what happened to our 2 unit vectors? And here, what happened to our 2 unit vectors is our y vector remained the same, right? And our x vector, instead of being originally here, like it was over here, it was rotated by 45 degrees. So now it's over here. So here's I. And because we've moved these 2 vectors that define all of the plane, now we have a new plane. And this is some random transformation, we'll call it R. And we've essentially, and I'm going to redraw this because this is really bad. So this is what our new space looks like, instead of just being our normal squares that we're all used to. Yeah?
How do you mathematically describe the rotation of a unit vector?
Yeah, that's a good question. And actually, I was just going to get into that, yeah. the way we describe this like rotation or any, not just any rotation, but just transformation in general, is by the matrix. So, and the matrix is, and I'm gonna stick to just a 2x2 matrix here. So it's a set of 4 values, A, B, C, and D. And what these 4 values represent is A and C, and I'm gonna draw a little line in between, so we just take a look at the first part. So we take a look at the left part here. A and C, this right here tells us where our new I hat is, so I hat prime. And this right here tells us where our new J hat is, so J hat prime. And because we're given the information of where these 2 vectors land, we can be given the information of what our entire plane looks like, where every vector in the plane lands, just based on these 2. Does that answer your question?
Yeah.
Okay.
Thank you.
And so, yeah, essentially this is what it is these coordinates, or these like values right here, just give us instructions, say, okay, take our original I hat, which was fixed at 1, 0, and we're gonna move it now to AC, whatever that is. Take our original J hat, which was fixed at 0, 1, and now we're gonna move it to BD. And so whatever that could look like, that could be a rotation, that could be a scaling, that could be a combination of, yeah.
Wait, so you never actually describe the changes to a specific angle, you can calculate the angle once you're just given the different like shifts of the endpoints of the
Yeah, I mean,
vector,
you can describe it with an angle, but you could also just say, instead of I hat in this case where it was rotated 45 degrees, instead of I hat being fixed at 1, 0, now it moved up to 1, 1. And that's all I'm saying. So there is a 45-degree angle.
Yeah, I guess you could still calculate the angle. It's just like,
yeah, you could totally calculate the angle. I just yeah.
But they just usually just do it just in terms of the difference in the number, like.
Yeah, just the number itself, and just say, okay, where do the 2 vectors land? And that's how our entire space looks like. So we could have space that looks like weird lines, and then like this. It could be anything. We could even have space, or plane, squished onto a single line. We can actually describe a transformation of our 2D space using these 4 values and just squish it onto a line. And the way we do that is we just say, well, and here's our origin. I hat remains fixed in place, and J hat, this is where J hat originally was, just moves down to I hat. And so the way, how we would describe this, the exact numbers of this matrix would be, let's see, I hat remains the same, so it's 1, 0, 1, 0. So, yeah.
Like, couldn't you just describe it in terms of just one of the variables then, if you had them combined into a straight line like that? Like, would there be any reason to describe it as the 2 separate ones, like in terms of both I and J, or could it mean you just have a higher magnitude of either one if they're on the same line?
Yeah, I mean, so in this case, actually, this touches on something completely different. But yeah, you're right. In this case, actually, you wouldn't have to use both I and J. You would just use I, because, and you could scale I. You can make this bigger or shorter, whatever. But yeah, this actually touches on something completely different called a non-square matrix, which I'll get into later on. Time for that. But in general, the matrices are what describes our transformation in space. And we don't even, and the reason, all this stuff, we just add values, our transformation is always going to be, we're going to have straight grid lines, right? All of our grid lines are going to be straight. They might not be parallel, they might not be perpendicular, but they're always straight. And, these grid lines are always parallel, but whatever. But there's actually, you can actually go further, and if you combine this with like multivariable calculus, you can actually have like transformations in space which are really weird. Like you can have like squiggly lines like this and like going random directions. And this can be actually something you can describe using a matrix. But when linear algebra only focuses on the linear transformations, not these weird non-linear transformations. Yeah, and that's pretty much it for this lecture. I think next time I'll touch on non-square matrices. That'll be the entire lecture. It's just transformations between dimensions. But now this is pretty much it. It's just the concept of transformations in space and the matrix.